Hello. You know what? Let me turn off my camera. Today we will work on some problems from this section 16.4. That's on Green's theorem. Let's review a little bit what is Green's theorem. Green's theorem says that, the theorem says the following. Integral of a closed curve positively oriented counterclockwise and then close and then smooth and then simple curve C of vector field F dot dr. This is equal to double integral over domain D, which the closed curve C encloses, of Q sub x minus P sub y dA. Okay, so let's say D is this region here, this is region D, and C is the smooth, piecewise smooth, and then what else? Close and then simple, positively oriented curve C enclosing D, region D. Okay, so we usually denote the C here, the closed curve C, as the boundary of region D. That could be the notation. Okay, of a vector field F with continuous first derivative on an open region containing D. So when we say open region containing D, we are talking about a region containing D and also including the boundary, a bit over the boundary, or more, of course, right? Basically, this way we guarantee that the vector field has continuous first derivative even at the boundary C. Okay, because for that to be differentiable there, then you must have a circle whose derivative exists from every direction, right? I hope you remember that. Anyway, so we have that formula. And one of the big consequences of Green's theorem is, for example, to find the area of region D. Okay, the area of region D, which is actually double integral over D of dA, right? Now, that can be seen as, if we apply Green's theorem, that can be seen as a integral over closed curve of C. You go backward, right? But you set the Q, that's Q sub x minus P sub y equals to 1. We can say that Q sub x equals to 1 and then P sub y equals to 0. That means the Q is x, right? And the P is 0. Okay, so we get the F is 0 x dot dx dy. Right, this is the vector field F, and then this is the dr. Or basically, if we put things together, this becomes integral over closed curve C of x dy. Using the similar trick, but instead we use Q sub x equals to 0 and P sub y equals to -1. So q is 0, but the p is negative y. Then we will get integral over closed curve of c of negative y dx. Okay, now, or you can also add those two and then divide it by 2. We get 1/2 of integral over closed curve c x dy minus integral over closed curve c of y dx. Okay, now that's for the formula for the area. Now, even though it may not be that super useful for right now at the beginning, the way we find out, compute that, enable us to do something else later on. I think we can find the moment of with respect to x-axis or respect to y-axis using a very similar technique. Okay, but of course the closed curve integral, the line integral over c becomes different. We talk about that later. Okay, let's hit the Green's theorem, applying this Green's theorem from this 16.4. Let's see number 2. The question is, evaluate the line integral using two methods. First one by directly, and second using Green's theorem. You see that Green's theorem is a lot easier, right? So let me do it by Green's theorem first. Okay, so C, the closed curve, is a rectangle with vertices 0, 0, 3, 0, 3, 1, and 0, 1. Okay, that's the rectangle. Let me use red color. And the assumption is it's a pot is positively oriented, right? So what is part B? What is double integral over closed curve of C of xy dx plus x squared dy? Now notice that if we look back, then this is the same to say this is integral over closed curve of C of the vector field xy comma x squared dot dx dy, where this is our vector field f and this is our dr, right? Okay, now according to Green's theorem, this is equals to double integral over the region it encloses D of q sub x minus p sub y dA. Okay, this is q sub x minus p sub y. If you remember our to show that the vector field in 2 dimensions is conservative, you need to show that p sub y equals to q sub x, right? Which, if you think about it, this is basically the guy we have in the middle here is actually the axis, or the difference between these two components here, these two partial derivative. Okay, the axis of conservativity, maybe you call that. Now, so this is equal to integral, let's do that, integral from 0 to 3, integral from 0 to 1 of x dy dx. The domain is rectangle, and then the integrand is separable, so we can just integrate that right away, huh? So this is 1/2 x squared from 0 to 3 times the length of y1. That's equals to 9/2. Okay, that's according to our Green's theorem. Now, if we do it one by one, step by step, path by path, which we expect to be a lot longer, right? Then we need to call, let's call this first. This is the first path, the second path, the third path. Remember, because the orientation is important, we need to keep the direction. Okay, so the first path, that is y equals to 0, the x is between 0 to 3. It would be nice if you can parameterize that. Let's call that r1. Okay, the from t comma 0, the t will be from 0 to 3. I think that would be better doing it that way. Okay, so r1 prime t will be just 1, 0. Okay, and then the integral over gamma 1 of x y dx is 1 dt, right? 1 dt plus x squared dy. I'm sorry, 0 dt. This is equal to integral. No, I should not use gamma 1 anymore. This is from 0 to 3. So this is integral from 0 to 3 of t dt. That's 1/2 t squared from 0 to 3. That's 9 over 2. That's for just lambda, gamma 1. Now let's see gamma 2. Gamma 2 is, if I parameterize that r to t, the x is already 3, but the y is from 0 to 1, linearly. Okay, so the integral over that path will become integral from 0 to 1 x y dx, but r, let me write it here. I'm supposed to have done it earlier. So r2 prime t will be 0, 1. Okay, so dx will be 0 dt plus x squared, that's x squared is t squared, dy is 1 dt. That is equal to integral from 0 to 1 of t squared dt. That's 1 1/3, huh? Yeah, that's 1/3. Okay, now how about gamma 3? Gamma 3, the third path, denoted by RT, that is the y already 1, but the x will be from 3 to 0. So 3 minus t, the t will be from 0 to t. Remember, the direction is important. So r3 prime t will be negative 1, 0. So the integral from 0 to 3 x y dx plus x squared dy. This becomes integral from 0 to 3 of t minus 3 dt. The second term is 0, right? Which will give us 1/2 t cubed minus 3t from 0 to 3. Oh, I'm sorry, this is t squared, not t cubed. That's 9/2 minus 9, that's negative 9/2. Am I okay so far? Okay, now then gamma 4, we are not done yet, we are not done yet, we are not done yet. For gamma 4, and pull a line here. The parameterization for R4T will be the x already 0, but the y will come from 1 to 0. So r for prime t will be 0, -1. Integral from 0 to 1 of x, y dx plus x squared dy. That is equal to integral from 0 to 1, pull the negative out, 1 minus t squared dt. Actually, I will do substitution. This is integral from 1 to 0 with negative. This is u squared negative du. Okay, is it right? So this is equal to so negative integral from 0 to 1 of u squared du. That's negative 1/3, huh? Why I get, hold on, did I make a mistake here? 2x minus x, supposed to be 9/2. Why did I get, I add, okay, I'm sorry. I think I might have made some mistake. X, y, x squared, x squared, x squared. Oh, here I make a mistake. X, y, and then it should be x squared here. So it should be x squared here, right? That's the question, x squared dy. So this should be 0 squared. So that's 0 squared, which is a lot easier. It should be 0. That is just 0. My bad. So this is equals to 0. Do I make a mistake with my computation? I'm sorry. Yeah, q sub x minus p sub y. Q sub x minus p sub y. That's x. Did I make, okay, let me show you first what makes me think it's something wrong. So integral over that closed curve C of f dot dr, that is equal to integral over gamma 1 union gamma 2 union gamma 3 union gamma 4 of f dot dr, which is equals to integral of gamma 1 plus integral over gamma 2 plus integral over gamma 3 plus integral over gamma 4 of f dot dr. And that's equals to integral of each, and that gives us 9 over 2 plus 1/3 minus 9/2 plus 0. That gives us 1/3. It's different value. That's why I say something not right. Okay, so let me compute my Green's theorem again. On the top one, that's fx squared. 2x minus x, that's x. The y is 0 to 1. Okay, the x will be 0 to 3. So the answer should be 9/2. Okay, I may have plugged in something wrong. Okay, I may have plugged in something wrong. So this is x, y, x, y, x squared. X, y, and this is, oh, the x squared. This one it should be, sorry, this one should be x squared. So this should be 3 here. Should be 3 here. Okay, so if that's 3, this is 3 then, x squared, no, 3 squared, 3 squared, 3 squared, that's 9. Okay, so that's not 1/3, but that's 9. X, Oh, this one is also 0. T times 0. What am I doing? T times 0. So this is 0. Miscomputation. Well, good thing I checked with my second method, huh? Yeah, good thing I checked. So too many miscomputation. So we get 0 plus 9. 0 for the first gamma, 9 for the second gamma, negative 9 over 2 for the third gamma, 0 for the last gamma. And when we add them together, we get 9 over 2, which is the same to the answer we have earlier. Okay, so at least now you see the benefit of using Green's theorem. It's shorter, simpler, tend to be less mistakes, right? Okay, and if we try to confirm that by doing that directly, you see I make computation mistake. My mistake is actually plugging in. You know, I keep on plugging in the incorrect one. This is my x, this is my y. X, y, x squared. X, y, x squared. X, y, x squared. Like that. Okay. X, y, x squared. You know, that's the issue. Okay, that's for number 2. Notice that I also purposely go over part A, computing directly, just to remind us how to do line integrals over vector field from the previous section. Okay, let's go on to the next one. Number 6. Use Green's theorem to evaluate the line integral along the given positively oriented curve. Okay, we see is a rectangle 0, 0, 5, 0, 5, 2, 0, 2. Oh, the same thing we have earlier, similar. Okay, it's positively oriented. Okay, so that integral over closed curve C of cosine y x squared sine y dot dr. I purposely write it this way so that you can see the vector field and where's the P, where's the Q, right? And then I can use Green's theorem over domain region D of Q sub x, that's 2x sine y, minus P sub y. P sub y, the derivative of cosine is negative sign. So that is equal to double integral over domain D of sine y times, you know what, I write the polynomial first, of 2x plus 1 times sine y. You know what, I break the D also at the same time. Call this dy dx. The benefit is 0 to 5 and then 0 to 2. The benefit is like the domain is a rectangle and then the integrand is separable. So this becomes integral from 0 to 5 of 2x plus 1 dx, integral from 0 to 2 of sine y dy. Okay, so we get x squared plus x from 0 to 5 times negative cosine y from 0 to 2. That's 25 plus 5, that's 30 times 1 minus cosine 2. Okay, that's for number 6. Let me circle it so that we know which one we work on. And then number 10, partition again. We have that integral over closed curve C of 1 minus y cubed x cubed plus e to the y squared dot dr, where C is the boundary region between two circles, between two circles. They don't say the orientation of the boundaries, okay? But the assumption is therefore that it is positively oriented, okay? Now you can see I do it this way. Let's say this is the orientation of the outer one, and the inner one must have this orientation. Remember, it is positively oriented if the region it encloses is on the left-hand side. Okay? The region it encloses is on the left-hand side. But Thomas, you know, this is not a simple curve. In fact, it's not simply connected. The region is not simply connected. So how do you justify the use of Green's theorem here? We can see it this way. Think of it this way. So the path, the curve actually looks like this, right? That's what it looks like. Now we will create a slit here that goes both ways. Now imagine if I travel in the following way. What color do I want to use? Let me use the green one. Imagine I start from here. I go positively oriented, right? And then to here, I go inside, go this way. Notice that it's still positive oriented, and then go back. So the green ones go in like this, and then come back here. Okay, now these two paths here, if I enlarge this, the path is opposite path but exactly the same one. So the line integrals, when you add those, the line integrals over those two, there must be canceling out each other. Okay, now once we see the closed curve, piecewise defined, simple, positively oriented curve like that, enclosing this region D, then we can justify the use of Green's theorem. Okay, think of it this way. From here I go, and then, oops, that's not what I want. That's not what I want. I don't want that to justify. And then it goes this way. No, that's not what I want. And then cut back in like that. Okay, so now that's the idea. So that just justifies why we can use Green's theorem. By Green's theorem, therefore, this is double integral over the blue region of q sub x. Do you see the benefit of this? Q sub x will give us 3x squared, and the e to the y squared suddenly becomes irrelevant, minus p sub y, negative 3y squared dA. Okay, which I can factor 3 out, double integral over d of x squared plus y squared dA. Why this is so nice? Because the domain is nice to be done using polar, and the integrand becomes a very nice integrand when we deal with that in polars. Integral from 0 to 2 pi, integral from 2 to 3 of r squared, r d theta, independent of theta. This is 3 times 2 pi, right? That's r cubed becomes 1/4 r to the 4th from 2 to 3. Okay, so we get 3/2 pi, 3 to the 4th is 81, 2 to the 4th is 16. What's that? 65? Well, anyway, 3 times 65 over 2 pi. Is it right? That's 195. 195 over 2 pi. Okay, so it is crucial for you to set up the integration properly. Do not rush to the integral. set it up properly first, okay? Because anything wrong with your setup, please take heed of my suggestion, my input here. Okay, I have seen too many. Okay, I have seen too many people rush to the integrations. They didn't set it up properly, thinking that you can set it up properly later on, just to find out after the test, sadly, that they set it up incorrectly, and the integral becomes too hard to do. Okay, I can give you easy questions, but then if your setup is incorrect, it becomes hard questions, and then you may blame me later on. That's not fair, right? Okay, yeah. You see the mistakes I make up here? It's silly mistakes if you think about it, right? But notice that I already spent so much time just to later on figure out, oh, good thing I have part B though. You know, good thing I did part B first to identify that, oh, you know what, my answer originally must be wrong, so I can check my work. But I would not be checking my work if I did part A first without doing part B. Okay, yeah. Why? Because I did a simple silly mistakes. Okay, yeah. I have seen too many of that, and you have seen that also from me earlier, right? Okay, so be very careful with your setup. Okay, let's see the next question, number 14. Use Green's theorem and check the orientation of the curve before applying the theorem. Okay, number 14, we have this vector field. C is the triangle from 0, 0, 1, 1, and then 0, 1, and then 0, 0. Okay, that's positively oriented. Okay, so the integral over closed curve C of f dot dr is equal to double integral over region D of q sub x. What is the derivative of tangent inverse x? 1 over 1 plus x squared minus the derivative of that's 1x over square root of x squared plus 1 dA. It depends on x only, huh? Which is very nice, which means, okay, this will be double integral over D. If I, that's 1 minus x square root of x squared plus 1 over 1 plus x squared dA. I don't think I make a mistake here, but why it seems like it's a very hard integration? Well, hold on, it's not supposed to be. Yeah, it's not supposed to be. You know what? It may have something to it seems to be how to say that. Maybe not doing this for now. Because this is the derivative, and then when later on we integrate that, we basically get that thing back, right? But it may have something to do with the domain. If I look at the domain, I think I will want to do in terms of y, 0 to 1 for the dy, and then for the x will be from 0 to y of 1 minus 1 minus x squared is x over. Let me give myself some space here. It's too small. So this will be minus x over square root of x squared plus 1. Oh, because I do respect to x first, right? So when I do integrate respect to x, that will give us tangent inverse x, right? Minus square root of x squared plus 1 from 0 to y dy, right? And then this will be integral from 0 to 1 of tangent inverse y minus tangent inverse 0, which is 0, okay, minus square root of, if I replace that by y, I get y squared plus 1, and if I put 0 there, it becomes plus 1. That's what I get. Okay, now how to integrate that? That's another story. I wonder. I don't like to do this one. I don't like to do this one. Let's see. Let me do a side note here. Integral of tangent inverse y dy. If I do the derivative here, it's 1 over 1 plus y squared. This is y. So the first integral will be y tangent inverse y minus from 0 to 1 minus integral from 0 to 1 of y over 1 plus y squared dy. That's for this part. This integral gives us this. Okay, and then minus, what is the integral of that thing? I think I need to do substitution, huh? Should I do substitution? I don't know. Is there a special integral for that? So if I use y equals to, y has to be tangent, theta. So dy is secant squared theta d theta u, and then square root of y squared plus 1, therefore is secant theta. So that becomes integral from 0 to 1, 0 to pi over 4 secant cube theta d theta plus 1. You know what? Let me say that this guy here give us this. Okay. The first one is 1 tangent inverse 1 is pi over 4 minus the integral for this is natural log of 2. You know what? Let me slow down a little bit. Okay, so if I use w equals to 1 plus y squared, dw will be 2y dy. That's where I get the 1/2. Okay, and then natural log of absolute of w from 1 to 2 minus, what is the integral of secant cube? Integral of secant cube is 1/2 times secant theta tangent theta minus natural log of secant theta plus tangent theta. I think it should be plus, like that, from 0 to pi over 4. So this will be pi over 4 minus 1/2 natural log of 2 minus 1/2 times radical 2 times 1 plus natural log of radical 2 plus 1 plus 1. I'm so lazy to simplify this, but I guess I still need to. So pi over 4 minus natural log 2 over 2 minus radical 2 over 2 minus 1 natural log of absolute of 2 plus 1 over 2 plus 1. Simplify further yourself. I may have made some miscomputation somewhere in between, but I kind of get bumped here. To integrate that, I need to do integration by parts for the first part, which I don't think is too hard. But I'm not really sure the integral of secant cube theta though. I forgot, but let me derive it. Integral of secant cube theta d theta. Just a side note. Okay, this is integral of how to do this. Secant theta times secant squared theta d theta. The derivative of secant is secant tangent theta. The integral of secant cube is tangent theta. So according to integration by parts, that is equal to secant theta tangent theta minus integral secant theta tangent squared theta d theta. If I call this I, this is secant theta tangent theta minus integral of secant theta times 1 minus secant, no, actually secant squared theta minus 1. Secant squared theta minus 1 d theta. So this becomes 2i secant theta tangent theta plus integral of secant theta d theta. Okay, so I is 1/2 secant theta tangent theta plus the integral of secant theta is natural log of, oh yeah, that's right then, secant theta plus tangent theta, of course plus constant, right? That's the integral. Okay, so I get it right. The integral from 0 to 1 of 1 is just 1. Okay then, I think that's it. Okay, let me cover this. It will only show up on my recording but not on my notes. Okay, number 22. Let D be the region bounded by closed path C. Let's say this is the D. Of course, we want to make the boundary to be smooth. So this is the C. Simple closed path C on XY plane. This is our D, and this is curve C. Use Green's theorem to prove that the coordinate of the centroid of D are, okay, the centroid, the formula for the centroid is the x bar equals to the moment with respect to y-axis over the mass, right? But the mass is equal to the mass of D is equal to its centroid, so the density is the density is constant. The density is constant. D, yeah, constant. Just call that D then. Okay, so the mass will be double integral over D of density dA, which is basically density times the area of D. Okay, however, how about the moment with respect to y? The moment with respect to y is double integral over D of x density dA, right? We can factor the density out, double integral of x dA. Now, call this guy x here as our q sub x minus p sub y equals to x. Now we can assign q sub x to be x and p sub y to be 0, right? So p will still be 0, but our x will be, if we do the integration, that's 1/2 x squared. Okay, therefore, this integral, according to Green's theorem, is density times integral over the closed curve C of 0, 1/2 x squared dr. Which will give us density integral over closed curve C of 1/2 x squared dy. Therefore, if I continue here, then dx bar equals to, I need more space. Dx bar equals to density integral over closed curve C of 1/2 x squared dy over density times the area of D. Okay, notice that the density cancels. I can bring the 1/2 out, and we are left with integral over closed curve C of x squared dy. That's for the x bar. Now you can try your y bar the same way. Okay, you can try your y bar the same way. That's for number 22. Let me go on a little bit more. Number 20. Yeah, number 28 is the last question. Okay, so calculate the closed curve integral of C of f dot dr, where the f, the vector field, is x squared plus y, 3x minus y squared. Therefore, the q sub x minus p sub y will be 3 minus 1. That's 2. Of C is positively oriented boundary curve of region D that has area 6. Well, according to Green's theorem, this will be double integral over D of q sub x p sub y dA, which is 2 integral, double integral over D of dA, but this is basically 2 times area of D, which is given there to be 6, so that integral must be 12. Okay, that's for problems from this section. I believe I have done enough problems from this section in the lecture videos, so our supplemental videos not a lot. Green's theorem tends to be a very small package, you know. Okay, that's for 16.4 exercise for your supplemental video.